In this next series of videos, we're going to look at base-promoted elimination reactions, which are related to nucleophilic substitutions because they involve the same types of substrates. This sets up a really interesting situation where, under a given set of reaction conditions, substitution, elimination, or even a mixture of the two may occur to give different products. As in nucleophilic substitution, there's this mechanistic dichotomy between bimolecular and unimolecular elimination as well, and in cases when we know elimination is operating, it's straightforward to distinguish between the E2 and E1 mechanisms using ideas that we've seen already for SN1 versus SN2. In fact, as we'll see, E1 and SN1 share a common carbocation intermediate and a common first step. In general, elimination refers to a reaction in which two groups linked to adjacent atoms, typically carbons, are removed from the substrate, leaving behind a pi bond and potentially a new XY linkage. This is the opposite or the reverse of addition, in which X and Y add across the pi bond. In base-promoted eliminations, one of these two groups, say X, is a hydrogen atom, and the involvement of a base promotes elimination through the donation of electron density to this hydrogen, which is somewhat acidic in cases when Y is a good leaving group, such as a halogen or a sulfonate. Here's an example of a base-promoted elimination reaction. Within the substrate, we can identify a few things. First of all, this is an alkyl halide. It's an electrophilic alkyl halide that could, in theory, engage in nucleophilic substitution. But when the alkyl halide has hydrogens at the beta position, that is, linked to the carbon adjacent to the carbon bearing the leaving group, the possibility of elimination exists as well. Just as in nucleophilic substitution, in base-promoted elimination, a leaving group or nucleofuge departs with a pair of electrons. Here that leaving group is chloride. Unlike nucleophilic substitution, the anionic species here doesn't donate electron density to the electrophilic carbon. Electron flow like this would lead to an SN2 nucleophilic substitution process. But in an elimination reaction, this anion goes for this mildly acidic hydrogen at the beta position. As a result, the electrophilic alpha carbon receives electrons not from the anion directly, but from this CH bond, forming a new pi bond between the alpha and beta carbons. In this reaction, isopropoxide is acting as a base rather than a nucleophile. It's donating electrons to a hydrogen rather than a carbon. An important byproduct of this reaction is the conjugate acid of this base. In this example, it's the molecule isopropanol. A second important byproduct is the conjugate base of the leaving group or nucleofuge. Here, chlorine departs with a pair of electrons, so that Cl- is formed as a byproduct. And this anion will always be some kind of stable anion, as we saw for nucleophilic substitution. Finally, electron flow from the CH bond between the alpha and beta carbons leads to the formation of a new pi bond, or an alkene functional group. Base-promoted elimination reactions bring up all kinds of interesting questions. For example, not even thinking about nucleophilic substitution, we can ask a question about substrates that have distinct beta hydrogens. What happens when we have two distinct sets of constitutionally heterotopic beta hydrogens, as we do in this molecule? This hydrogen that I'm highlighting in red is constitutionally heterotopic with respect to these three hydrogens I'm highlighting in blue. But both of these are beta hydrogens with respect to the carbon bearing the leaving group, which we call alpha. The central question here is, how can we predict whether the red hydrogen or the blue hydrogen will react? Another important question that we'll come to a little bit later is this issue of when elimination occurs in preference to or along with nucleophilic substitution. Notice again that our substrates are the same: tetrahedral alkyl halide or pseudohalide, and something with a reactive anion or a reactive pair of electrons that can act as either a base or a nucleophile. The reaction conditions, at least in a naive sense, considered not very deeply, for substitution and elimination are the same. So how can we use features of the nucleophile, electrophile, and reaction conditions to determine when elimination will be favored over substitution or vice versa? We'll explore this question in detail as well.